this abstract array-based language. Now, I should note.
Can you stop for just a minute? The Microsoft Teams just became available. So hello, everybody, and welcome to our meeting. Sorry for the slightly late start. Ezra Stein is here tonight, and he is going to be telling us about CUDA's new tile library. Since it was taking a while for Teams to get started, we've already covered the first few slides, which mostly just said, what are the wonderful things that GPUs can do for you? What are some of the use cases? And now he's going to talk about what this new library can do for us.
Great. And can you all see my screen? Is that visible? Yeah, on the Teams meeting. Okay. All right. So I guess just to recap, the idea is with Tile C++, the programmer writes essentially a single-threaded program with array-based operations, and the compiler will parallelize them across the GPU threads. I should say this isn't exactly a new idea. There's lots of languages that have array-based programming, such as Fortran and MATLAB. And there's some languages.
By the way, Ezra, your mic is off.
Oh,
can you please turn it on so that people can hear you?
Sure. Okay, can you all? All right, you can all hear me?
Yes, we can hear you now. Thank you.
All right, great.
Please continue.
Yeah. So I'll say there are existing languages that do this. However, this is the first major implementation in C++ that targets a GPU. So that's what's pretty exciting here. All right, so in order to understand sort of how this all works, we have to look at how the GPU core works and how it's evolved over time. So at the most basic, a GPU core contains one or more or several streaming, or a GPU contains several streaming multiprocessors, which is what we call a GPU core in NVIDIA's terminology. Usually there's like tens to maybe 100 or so of these GPU cores. Within one of these are lots of little arithmetic units or hardware threads. And sitting alongside the GPU, you've got your global memory and DRAM. And now this DRAM is generally pretty slow to access. So before you can really do much with the memory, you typically want to cache it locally into the GPU core. This cache is called shared memory. So already with just these three abstractions, these are all exposed directly to the programmer. So they have to manage all of these resources and coordinate between them. This was sort of the state that GPUs were in about 10 years ago. And since then, it's actually only got more complicated. So in around 2017, NVIDIA GPUs added a new hardware unit called a Tensor Core. This is specifically designed for performing matrix multiply operations, which show up in a lot of domains. And in 2022, we added something called a TMA unit. This is a specific hardware unit that asynchronously copies between your global memory and your shared memory cache. So in general, this unit can be running simultaneously with all those hardware threads. So to get good performance on the latest GPUs, you want to overlap your computation, which is happening in the hardware threads, with memory copies that are pulling in data for the next part of the application. And finally, in 2024, the more enterprisey GPUs added something called Tensor Memory, which is another layer of caching that specifically lives in the Tensor Core for holding the data for the matrix multiplication. So in order to manage all of these resources, you'll probably end up writing code that looks like this. So this is some code that performs a sort of general matrix multiply on an arbitrarily large matrix. And I wrote this up in preparation for the talk. I'm not going to go through it in too much detail because it's quite complicated, but I do want to point out a few things. So here is some code that manages that shared memory resource. These are declaring variables with a particular shared keyword. Over here, we've got some inline assembly. This is issuing what is called the Tensor Core instructions. I should note that these instructions have changed just about every year, and they all have different constraints, such as the sizes of matrices they can work with, whether they're synchronous or asynchronous, whether how many threads need to cooperate when performing the instruction, and so on.
Different assembly for different GPUs?
Yes, exactly. And that's one of the major issues. And over here, we've got some Tensor Memory Accelerator code. So this is what's asking that TMA unit to initiate a global memory to shared memory copy. We also need for TMA some code that sits and actually runs in the CPU, what we call the host. in order to manage the metadata around what pieces of memory to copy and the shapes and so on. So there's quite a lot that needs to be coordinated in order to even get that unit to work. And finally, we've got multiple threads which are running concurrently, doing different things, and they have to signal to each other. One set of threads that does the memory copy needs to say, hey, I've finished copying the memory. You can begin the computation on that memory now. So what I've highlighted here is a bunch of these synchronization primitives, which we call M barriers, and it's sort of littered throughout the code, and it handles all of that signaling. So if we just step back and look at this, the actual matrix multiply is nowhere to be found in here. It's all just managing these low-level hardware resources. So to recap, the major problems with this programming model are the complexity. We have to manage the hardware resources manually. In addition, we have to, in order to get good performance, pay attention to all of these little details. Since these hardware units are sort of not ideal systems, you have to look through the assembly instructions and the specifications in order to get good performance. And there's lots and lots of techniques here that, take a long time to learn. So overall, this makes GPU code difficult to learn and to debug and to write, and it inhibits adoption of GPU programming in general. And the other major issue, as you pointed out, is portability. So every time we introduce a new GPU, there are new hardware units that are involved. So you potentially have to write different assembly instructions to exercise those hardware units. And to make matters even worse, sometimes we remove hardware units in a new GPU generation. So not only will your code not necessarily perform well on the newer GPU, it might not even run at all. So this is not a great place to be in. This means essentially you have to rewrite your algorithm every year if you want to get the best performance on the GPU. All right, so here's how Tile C++ can help. This is the same code, but written in Tile C++. It's performing a matrix multiply. And I'll walk through all of this a little bit later on in the talk. But the takeaway here is that this reads essentially as single-threaded code using a algorithmic, just traditional procedural algorithmic code. So there's no hardware resources involved. The compiler handles lowering this to essentially the same program that I showed on the earlier slide. So we'll get into the techniques for doing this, but this can give you good performance in hours instead of days, and it works across all of the GPU architectures. So the compiler handles those details. So before I can really explain sort of how the lowering step happens from this high-level description to the lower-level stuff, I want to talk a little bit about how we traditionally program GPUs, get a little bit more into the single instruction, multiple thread programming model, which is what CUDA C++ implements. So if we look at how do we design an algorithm for SIMT programming, the first step is you've got some data that you need to process, and you have to chunk up that data into different blocks that are going to be processed independently. The purpose here is your GPU is only some finite size. It can't process all of your data concurrently all at once in the GPU core. So if you want to process a large amount of data, which won't fit necessarily in your GPU, you chunk it up into pieces. The GPU pulls in a piece, processes it concurrently in the GPU, commits the result, and then it's ready to pull in the next piece and continue going. So this is how you scale your program to arbitrarily sized amounts of data, and it's sort of inherent to GPU programming in general. So this step doesn't actually change with the Tile programming model. You still chunk up your data into blocks. However, in the SIMT model, within a block, you then use threads to perform the computation. And there's a number of ways to do this. You can assign threads to different pieces of data, have them all run and perform their own computation, or you can have them cooperate together. So they could do a reduction, they can synchronize with each other to exchange data, and so on. So once you've done this, you have an algorithm that runs on the GPU, but it doesn't necessarily perform well, and we'll see why. And so let's walk through sort of how we apply this to matrix multiplication. I'm using matrix multiply here just because it's pretty good at exemplifying all of this, but these principles apply in general to any GPU application. So as I mentioned, the first step is to chunk our data set up into blocks. So I've got my left matrix A, which has some size m by k, and I've got my top matrix B of size k by n, and my output C. the most natural way to sort of chunk up the data set is to say, okay, some piece of C is going to be some block that we want to compute, and we'll just look at just that piece of C that we want to compute for that block. So if we do this, you end up with something like this. So this is an example of one block of our output data that can be processed concurrently on the GPU. And we can take a look at what data from our inputs contribute to that. So that's going to be these rows and columns that are highlighted here. So our application is going to run on different blocks. So all we really need to do is focus on what happens in a block. So we can zoom in here. And the next step is to figure out how we want to use the threads of the GPU to process this block. In this case, the most natural thing to do is we could just say, well, we have different elements in our output, so let's just have one thread process a different element. And then the threads don't really need to talk to each other, and it all works out nicely. So if we do that, you get something like this, and we can highlight what one of those threads is doing. It's essentially doing the dot product between one particular row, one particular column of the inputs. All right, so let's dig into the code that implements this. So this is the naive matrix multiply. It's sort of the simplest algorithm you can use for matrix multiply on the GPU. And I'll just walk through a little bit about how this works. If we look at the very top, we've got our inputs. So the pointer, A pointer, the B pointer, those are pointing to memory regions that contain our data, M, N, and K, and our C pointer, which is the output. So I should note that when a block runs, it starts executing this code, and it pushes all the threads to run the same code. So multiple threads are going to be executing this simultaneously once a block starts running. So the first step is all the threads construct this MD span. So you may be familiar that MD span is a C++23 library feature, right? It's essentially a pointer to some memory and some shape associated with it. So it's just a nice abstraction around, some array in memory. So they construct this, it produces the shapes on the bottom right. And then the next step is to figure out which block is executing. So some block was selected by the GPU to run. That's done with this code right here. This is getting the block index, and it's determining which block, which part of the output matrix we need to process, because it determines which block is currently executing. And then we need to figure out which thread is currently executing. So many threads are running this for the block. So the thread index is used to make that determination. So once I have that information, I can figure out what output I want to write, and I use the for loop to perform that dot product. Finally, I commit the result to memory. So we can take a look at the performance of this code. So I have a bar chart here, which is showing two things. We have the naive SIMT, which I haven't shown yet, and we have on the right the performance of CUDA on a large matrix. And I'm running this just on my a consumer GPU that's relatively new. Yes, good question. So CUDA is a library that NVIDIA authored, which is very highly tuned for matrix multiplication. So there's a lot of engineers working on CUDA that are essentially making it the most optimal library that you can use to perform matrix multiply on any GPU architecture. So you can sort of think of CUDA as the best we can get. So if we get close to it, that's pretty good. So in this example, CUDA is taking about 9 milliseconds to run, and we can look at how well our naive SIMT application does. It's about 550 milliseconds, so way, way slower, like 2 orders of magnitude. So this is not great. We sort of just naively, applied our, way of constructing an algorithm on the GPU, and this is what we got, which is not too fun. So what's going on here? Well, this is where you start to have to understand the hardware of the GPU. We can take a look at what the memory access patterns are for each of the threads. So if we look at, let's say, this first thread that's processing the block, it's working with this top left element, and it's going to load some data from A and B, like a row from A, a column from B. And each time it loads some data, it's accessing that global memory, right? These arrays are very large, and so they're living inside this global DRAM memory. And as I mentioned, global memory is very slow to access. There's a lot of latency to pull in the data. And we can look at what the next thread is doing. So it's also accessing the same row of A, but a different column of B. And the third thread is also accessing the same row of A in a different column of B. So what we see here is that different threads are pretty much accessing the same pieces of data. So we're paying that cost of loading from global memory multiple times. So you may know what the answer is here. It's to cache the memory locally so that when we reload the same piece of data, the load is fast. It's in the cache. Now, the first problem is our cache is pretty small. In general, the GPU cache, it's not going to fit an arbitrarily large data set. And in this example, the K dimension, that's some runtime value that the user selected. It's not going to fit in the cache if we just try to pull the whole piece of data and put it in there. So we use a technique called tiling. And this is sort of where the name Tile C++ comes from, because this technique shows up in the programming model later on. But in SMT code, tiling, the idea is you take a piece of the data that you need to cache, you pull it into the cache, you do just the computation on that piece, you get some partial result, and then you pull the next piece of data in the cache and then do the computation on the next piece of data. So the way this would look is we would ask all the threads to read from global memory, take a piece of our input matrices, put it in the cache. We then perform that computation, and then we get some partial result, which we store locally. And then we move on to the next piece, cache that, do the computation, and so on. So we can take a look at how our improved algorithm works. So this is the code for it. Everything sort of at the top with MD spans and the block index, that's all the same as before. The first change is this line right here. So this is declaring a variable that lives in the shared memory space of the GPU. So that's what that _shared keyword is doing. The next step is we begin to enter our loop of caching data, doing the computation, and so on. So here we have the first step of that loop. So on the right-hand side of these assignments, we're loading data from global memory. Each thread is taking a piece of that global memory, and then it's assigning it into that shared memory cache. And the interesting thing here is after we've done that load and store, we have a call to this function called sync threads. So this is important. The sync threads line, when a thread hits this, it waits for all the other threads in the block to get to the same point in the application. So you can think of it as all the threads wait there before anyone continues on to the next step. And we need this because the next step, our threads are going to start reading from that cache data set. And we have to make sure that all of the cache has been pulled in before we're ready to start doing computations on it, or else we may have a race condition. So this is the first instance where we see, okay, we have to manage the synchronization because now our threads are not just accessing data, different pieces of data, they're going to be coordinating on the same set of data within this cache. So if we move on to the next step, we will perform the computation, we'll get a partial result. And again, we have to synchronize because we don't want threads to race ahead and go on to the next step until everyone's done with the computation. So we can repeat this process a few times, and then eventually we're done with the whole matrix, and we can store the result. All right, so let's see whether we've improved things. So on the left, I got the naive SIMT. On the right, I've got the optimal cuPLOS. And in the middle, we've got our shared SIMT code. So it did better, but it's still nowhere near close to the cuPLOS performance. And the interesting thing here is that the algorithm I just showed, that used to be the algorithm for matrix multiply. About 10 years ago, this is what GPUs did. There wasn't a way to really do much better. You could do a lot of tweaking, but that was essentially the algorithm. However, things have changed a lot in GPU architecture. So to understand how to get better than this, we have to start looking at what hardware resources are being utilized by the GPU when we're performing our application. So let's take a look at that code again, and we can now look at which hardware units are active at any given moment. So in our first time step, we're performing some memory accesses, and then we have sync threads. So everything stops and waits for the accesses to finish. Then in the next time step, we do some computation. These are exercising the hardware units, right? The arithmetic units. And then again, a sync thread, so everything stops. Then we go back to memory access, and then computation, and so on. So zooming out a bit, this is sort of what the access patterns look like, the hardware resource utilization. And as I mentioned earlier, modern GPUs can actually overlap the computation and the memory access steps because we have this special unit called a TMA unit. So what we see here is while our memory access is happening for, let's say, tile 0, our hardware units are totally idle. And same with computation, when that's running, our memory access units are idle. So ideally, we should try to overlap these units. So this uses a technique called pipelining, and the way it's realized in GPU code is through the TMA unit and through what we call warp specialization, which just means using some threads to perform one kind of operation and different set of threads to perform a different kind of operation. So specializing what the threads do. So one example of this is we could have the first 32 threads start with the memory access. Once that's done, we can begin the computation on that tile that we just loaded. However, while the tile is tile 0 is being computed, we can begin the memory access step, the caching step for the next tile, right? These can run concurrently in the GPU. And then we can repeat this process. So once caching of tile 1 finishes, we can begin computation of tile 1 and caching of tile 2. And so we can keep overlapping this until we get to the end result. Now, this, of course, complicates things substantially because now we have some result that some threads are producing that is now needed by other threads, which need to consume the result. So the way this is implemented is usually through some sort of producer-consumer queue. So you have some threads pushing onto the queue, other threads reading from the queue, and you've got some synchronization between the two to sort of signal, hey, I've pushed my work onto the queue, you can now consume it. So that uses these M-barrier hardware primitives. And this gets us back to that code that I showed earlier. So an implementation of that warp specialization looks like this. And I've also added in the tensor core operations here. So the computation isn't just using the usual arithmetic units, it's now using that special tensor core unit as well. All right, so how well do we go? So here again, I have our performance numbers, and we can take a look at how well our tensor core does versus cuBLAS. And we do all right, about 94 milliseconds, but still nowhere near where cuBLAS is. So what's going on? Well, the answer is there's not really any great insight into why we're not doing so well. It's just that you need a lot of time to tweak the algorithm for the particular architecture, for the particular data set, in order to get all the way down to that cuBLAS level of performance. So just in the time I had to prepare for the talk, I didn't have, I wasn't able to get the kernel working up to cuBLAS level of performance, but ultimately cuBLAS is using some variation of this same technique. All right, so let's now move on to the tile programming model, right? So how can tile improve this situation? So if we think about how to design an algorithm in tile, the key insight is to sort of move from this SIMD paradigm where you're managing these threads over to SIMD operations, where you've got some data that you process in bulk using element-wise operations. So the first step is the same. So you first need to partition your data set into blocks that can be processed independently. And this is not really, specific to the programming model. It's kind of inherent in the GPU. The GPU is only a finite size. However, in the next step, within a block, you use those SIMD operations and you use arrays to process the data in bulk. And then the compiler handles the rest. So the compiler will analyze the whole program and will do all the optimizations I talked about earlier. So the caching, the pipelining, warp specialization, all those hardware specific details. All right, so let's dig in a little bit about how this programming model works. So here I have sort of the traditional SIMD program. In this case, it's doing vector addition. We've got 2 blocks, and we have a different thread processing each element of the block. This is what the code would look like. You sort of have scalar operations on the right-hand side, and you have multiple threads entering that function. And here's the sort of diagram for tile. So you still got multiple blocks, but you've got one thread in the block, and it's performing array-based operations. And this is what the code would look like. So there's some interesting things to note here. We have a new data type called CT tile. You can think of this just as that vector type. It has, it's parameterized on the element type, in this case integer, as well as a shape, which is, in this case, just one-dimensional 4 to indicate 4 elements. And then in the function, it's taking a copy of these two instances of this type, and it's adding them together. And this addition occurs element-wise. So some more details on this tile data type. It's got a compile time and dimensional shape. This is important because the compiler needs to understand how many elements are in this thing in order to properly parallelize it. However, it doesn't have to be one-dimensional. It can be multi-dimensional. So it can be a 2D array, for instance. This type has value semantics, which is maybe interesting because you might think that if you've got arrays that are, quite large, and, you could have 2D arrays that have, hundreds of elements in it, you might think that copying them around would be pretty, not great for performance, a lot of data copies. Well, it turns out this isn't necessarily the case because the compiler analyzes the program and it's going to distribute the elements across many different threads. So by the time it's done scheduling the program, each thread is only going to be copying a few elements at a time. And the compiler has a lot of visibility into how these copies are happening, and it can perform optimizations that remove redundant copies in general. So it's value semantics, but you don't need to worry about the cost of copying it around. The second thing is it's got element-wise operations, as I mentioned. So the code on the right is computing a hypotenuse of a triangle, and it's just doing this element-wise across 16 lanes of this tile. And finally, the compiler is going to determine how to map these element-wise operations onto the actual hardware threads. So this thread-to-value association is determined by the compiler. So we can take a closer look at how the compiler might schedule one of these operations. So on the left, I've got the same code. It's computing that hypotenuse. I've just reoriented it a little bit so it has variables. And on the right, I have one way that this could be mapped to sort of a SIMG paradigm. So this is one way that the compiler could map the program. So in this case, I have each element of the tile is being handled by a separate thread, and we'll have 16 threads running this section of code. And I say it's in registers because I'm using local variables here, which the compiler can often place into a register in most scenarios. Now, this isn't the only way. We could also have 2 elements be handled per thread. So in this example, we would have just 8 threads enter this code, but each thread would handle 2 elements of that original tile. And this is useful because the compiler can tune the register pressure and based on how many threads it wants to allocate to this particular tile and how much data you want each thread to process. However, as I mentioned, if you're repeatedly using data, you often want to put it into shared memory. So we could also place this tile into the shared memory region. So here we have these variables that are allocated in that cache, and we're using 1 element per thread. And we can also combine the techniques and use shared memory with 2 elements per thread. So this is useful because the compiler can then tune to what extent it wants to perform memory accesses versus the total amount of computation on a given thread, so the arithmetic intensity of the code. And if you're familiar with SIMG programming, you may notice that the compiler is handling all of the thread index computations. So there's this technique called memory coalescing where you have to be careful about which threads are accessing which locations in memory to ensure that the hardware batches them up and pulls them in together. That you don't need to worry about in Tile because the compiler will schedule it to ensure coalescing happens. All right, so how do we get some data into this sort of abstract tile data type, right? This tile, you think of it as, it doesn't necessarily live in memory, right? I can't, if I try to observe the address of it, then we'll be forced to materialize the whole thing into a flat location in memory, and that's not great. So you usually think of a tile as an abstract data type, and you want to get data into it through some other mechanism. Well, we want to give the compiler a lot of information about the types of memory access patterns so that it can do a good job loading the data in. Maybe it can use that TMA unit, for instance. So the first step in doing this is we create something called a tensor span. This is very similar to the MD span type that I showed earlier, There's some minor differences, which I could talk about if people are interested. But the idea with this is it's just a pointer to some location with the size information about the array it's pointing to. Those sizes can be passed to the either at compile time or at runtime. So this xtense line at the top, that's telling us what the shape of this array is. The first argument to the xtense is this 8 underscore IC. That's creating an integral constant, which the compiler can then use at compile time to optimize the program. The second argument is just some runtime length. In general, a tensor span can represent various layouts. So in this example, the default is just row major layout, but you can have column major or strided layouts and so on. Now, as I mentioned, tiles have a fixed known size. So I can't just take this runtime known array and load it into a tile. I first have to chunk it up into pieces that have some particular fixed length and then load those in. So that's what this next line does. So this creates a tensor span adapter or a view over the tensor span. There's various kinds of views. This one's called a partition view because what this one does is it presents a chunking of that tensor span to separate sections that have indices that we can load separately. So in this case, each chunk is 4 by 4, and we have, we can index into those chunks. So the final step is to actually load from one of these, and you use the sort of chunk index to perform the load. And the compiler knows everything about the memory access here. And so it can schedule this to run on the TMA unit or whatever the latest hardware, needs for performing that memory access. All right, so now we have everything we need to walk through the final matrix multiply algorithm for Tile C++. So I'm going to actually start on the right-hand side here because that's where most of the algorithm is. So if we look at this, the first step is to construct those tensor spans and partition views. So we're just creating a chunking of our input and output matrices. And this is useful because we only need to process certain blocks at a given time, right? Next, we need to determine which block we're processing. So this call to ctbid gets the block index, which is the the block that the GPU has decided to dispatch for the kernel. And then we enter the main loop. And you can see that this loop is very similar to our shared memory-based SIMT implementation of matrix multiply. We're sort of loading a piece of the data, right, into a tile. The tile can then be cached by the compiler, and we perform the computation on that tile and then commit the result. So here, the calls to load on the views are loading that tile, and then we have this call to MMA. That stands for matrix multiply accumulate, and it's sort of a high-level matrix multiplication. The reason it's an intrinsic is we want to map it to those tensor cores. So we wouldn't want to spell out the matrix multiply just as a series of additions and multiplications, because then it would be hard for us to recover the structure that this was indeed a matrix multiply. So this loop goes over a few times, accumulating results, and then finally we store the final result. So there are a few things I want to call out, which helps give this code good performance. The first is this loop right here is written in a special way. So you'll notice that we use a range-based for loop, and we have a data type called CTIRange to represent the range. The purpose of this is we want to give the compiler information about the iteration space of the loop. So this iRange, the arguments tell it about the lower bound of the loop, the upper bound of the loop, and there's an optional third argument for the step. So if we use this as opposed to sort of an unstructured for loop, we know immediately that, yeah, this loop has, a certain trip count, has a certain lower bound and upper bound. We don't need to go in and analyze the loop to figure that information out. Moving on to the sort of starting part of the application, all of this code is just setting up various information that the compiler can use. So the first are the restricted keywords here. You may know that this is useful for performance in CPU applications, but in Tile, it's especially important. And the reason is that those load operations that I showed, we want to run them asynchronously from each other. We don't want to have to do a load, then wait and do another load and so on. And if we think that the loads might alias each other, then we generally have to serialize them, and we can't run them asynchronously. So by declaring these pointers as restrict, we can schedule the program in a more asynchronous way. And I could talk about that in more detail later if people are interested. The next few lines here, these are declaring assumptions. So in this case, alignment of the pointers. We're saying that they must be 16-byte aligned, which is usually fairly reasonable on the GPU because our memory allocations produce 16-byte aligned pointers. In fact, I think even higher, maybe 32-byte aligned. And then the next couple of lines are saying that the lengths of the arrays are also divisible by 16. So the point of this is our TMA hardware, this isn't a perfect abstraction over it. It only works well for these 16-byte aligned types. So we have to tell the compiler, hey, this is 16-byte aligned, otherwise it'll use a more pessimistic version of the hardware. And finally, we've got the tile shape. So this is the shape that's being used when loading the tile from memory, those pieces that I showed earlier. So I've intentionally left the concrete numbers here outside of the program. The reason is that the numbers, the actual sizes of these tiles can have a pretty big impact on performance. And the sizes do change with different architectures. So some architectures are better with different sizes, some are worse. So we're not 100% portable in that sense. You do have to tweak your program a little bit to get the best performance for different architectures, but it's a lot better than before. You're not doing full algorithmic rewrites. You're just tweaking a few parameters. So I guess looking at this overall, it's much simpler than the corresponding SIMT code, which is quite nice. And as we'll see, it performs well. So we can take a look at how well Tile C++ does against cuBLAS. And there it is. It gets about 10 milliseconds compared to cuBLAS. And that's because it's doing all of the techniques that I showed, plus a lot more. So the last thing I want to talk about is the fact that Tile C++ is just regular C++. So it's general purpose. We support most of the language features, so classes, structs, unions, control flow, almost all control flow, pointer arithmetic and indirection. There's a few things we don't support. So there's no virtual dispatch, meaning virtual functions, virtual bases, function pointers, no recursion, and no gotos, coroutines, or exceptions. These are hard to work with because it makes the job of the compiler really difficult. It's hard to recover what the structure of the program is when you use some of these features. So you can use this today. It's available in the CUDA 13.3 toolkit, and it's fairly simple to use. I do want to point out that there are trade-offs with using Tile. You give up a lot of the low-level control, which is part of the point. But that means that you have to trust the compiler. So if the compiler doesn't do exactly what you want, you might not get the program you want. So that's why we don't really see CUDA Tile C++ as a replacement for the SIMT programming model. We really want it to coexist with the SIMT model. So in the way we've implemented this, within the same program, you can have both your SIMT code and your Tile code live side by side. They can, they're separate kernels and they can cooperate with each other. So you can use whichever one is best for the application. So with that, I think we can open it up to discussion and questions. And yeah, thank you all for having me.
Oh, thanks for coming. Just a second. Let's make sure that we can hear anybody who is talking. So please make sure your speaker is turned up. So if they have any questions, they'll be able to ask.
Yeah, let me mute myself.
So first of all, do we have any questions from people that are online? If so, please use the hand raise feature so we can see.
Do you have your mic?
I have my mic on now. I've just turned it on so I can ask that question. I'm going to turn it off again. The Tile version, the first half.
Yes. The Tile version first half. Oh, that's way too far.
So
okay.
part right there, big pointer. Why do we need to restrict on when all we're doing is reading?
Yeah. So in this case, it's really about that C pointer. So we want to make sure that C pointer, which is the one we're writing to, is the not overlapping with the two A and B pointers.
Okay, so restrict is saying C doesn't overlap with A and B.
Yep.
It's not saying that A doesn't overlap with B.
Well, yeah. I mean, it's saying that as a side effect, but the real important one is that C doesn't overlap with A and B because that's the one we're writing to. Yeah. You're right. If we only had reads in the program, we wouldn't necessarily need restrict because there's no way that we could, the data isn't changing, so we can schedule the loads however we want to. But it's because we have that one write that we need to worry about it.
Okay, the second question I wanted to ask, you said that there are some restrictions when using tile. Do those same restrictions apply to SINT or are they tile specific?
So some of them are tile specific, others apply generally. So the tile specific ones, virtual dispatch is not supported in tile, but it is supported in SIMT. So there is a notion of a function pointer on the GPU. It's not generally performant, but you can perform dynamic dispatch in actual GPU hardware. So that is supported in SIMT programming model. We don't support in tile mostly because the compiler would have a lot of trouble analyzing the program. So in order to do all of this fancy stuff, we essentially do a full program analysis. So we really want to see what is the totality of the program. And if we don't know where a given function is calling, then we can't inline it. We can't really do anything with it. Recursion as well is also supported in tile. Supported in SIMT, but not in tile. So it's a similar idea. We want to be able to sort of fully inline the whole program, get the full result of it. If you have recursion, you can't really inline it. Go-tos are supported in SIMT as well. We don't support them in tile though. The things which aren't supported in either are the coroutines or exceptions. So those aren't supported in either one. Oh yeah, TMA. So yeah, let me go back to that TMA hardware unit. Yeah, so I'll zoom in a bit. Yeah, so this TMA unit. So TMA is sort of a broad name for actually a few different things. So in the hardware, there's various instructions that do some type of asynchronous memory copy. We generally call them TMA. The way it works is in traditional SIMT programming, you have one instruction that asks the TMA unit, hey, begin a copy. And you also give the TMA unit a pointer to one of these barriers. The barrier is then waited on by some other threads. And when the TMA unit's done with the copy, it says to the barrier, hey, I'm done with the copy. You can let those threads continue. So it's a way for the TMA unit to then signal that those threads have completed their work. I think it's going to be hard to see, but the code here, so this is sort of initiating that TMA copy. And yeah, it's too hard to really see. But essentially this is asking the TMA unit to begin a copy, and then one of the M barriers will be signaled to indicate that the copy is done.
Any other questions from folks in the room?
Sure.
You use like CUDA malloc async or unified more custom tools?
Yeah, that's a good question. So that sits those APIs you talked about, that sits sort of at a layer above. So those are dispatched on the CPU, right? And they allocate some kind of memory. All of them are allocating that global memory that I talked about. The difference between them, so CUDA malloc async, right? That's saying we can on the host, we don't wait for the memory allocation to complete, right? So we can do it while some other device code is running. In this example, I was just using the regular CUDA malloc, so I wasn't using any special kind of allocation strategy. There's probably some benefit you could get out of this allocation strategy when you're using multiple different kernels and their kernels are talking to each other. But so far, what Tile is focused on is just like within the kernel, making that one kernel go fast. And then there's various strategies on top of it, which for coordinating different kernels together. I'm not too familiar with that quite yet, but sure.
Any other questions from folks online? Let's see, and I've got one more question myself. And
Sure.
towards the very end, you were talking about how we didn't show numbers for tile M and tile N, tile K. You said that we needed to determine them empirically. Is there anything to help us determine those empirically? And if we have to determine them empirically, we have to do the same thing for each different set of hardware and say, use these numbers on the 5090, use these numbers on the 4090, use these numbers on the 3080.
Yeah. So you're right. They are almost entirely empirical. There's some guidelines, right? Generally, the larger the number you can get that works on your hardware is pretty good, right? So the larger the numbers are, you give the compiler a little bit more flexibility, because the compiler can always split these into smaller tiles and sort of reorder your application on a smaller version of it. But it's hard for it to make the tiles larger, because that sort of bleeds into the programming model, right? You don't necessarily know if the load is safe on a larger tile, for instance. So generally, larger tiles are better. However, larger tiles can also potentially consume more resources on the system, and that can have other effects, like it can change the heuristics that the compiler uses. It can force like different types of it can by taking resources up in one area, you're sort of limiting the program in other ways, and it might not be able to get that the same performance. So yeah, generally you have to determine it empirically. The tools for doing so are still in the works. So we have some tools which we're working on, which are designed to, in general, sweep through a large search space of different parameters. Because it's not just the tile size that you can tweak. There's various other things. I haven't shown it here, but you can attach these hints to various operations that try to guide the heuristics of the compiler. And those hints have a lot of different values, and they can also be tweaked. So you have a very large parameter space that you might want to search for, and doing an exhaustive search over it is usually not feasible. So there's more advanced searching algorithms, right, that try to figure out, okay, if I move in this direction in the search space, did that improve things or not? If not, I'll try a different direction. If so, I'll keep going in that direction. So sort of like gradient descent. So there's algorithms which try to explore these search spaces, and we're working, we have a tool that does explore that search space. So you can hook it up to this and have it sort of explore a pretty large search space for these parameters. But yeah, at the end of the day, the different architectures will require different parameters in cases.
Just kind of follow up on that. You got really close there. I mean, 10 to 9. That was awesome. If you don't tune those parameters, you still get correctness. Is that right?
Yep.
And then how much is if your parameters are off and you just use the parameters and the new architectures evolve, how much do you remain close to that? I forgot what it's called, the ground truth versus those earlier, which were order or two of magnitude. Is it 50%, 100%? Are you still pretty good with, or is that 10 really need all of that parameter fine tuning? And if you don't have it, you go back on the left side of this chart.
Yeah, I'd say, so I did tune the parameters for this example, and over the parameter sweep I used, nothing was worse than the next layer below. So nothing was worse than my handwritten one. So it was always within the order of like, I think, as good to like 3 or 4 times slower than Kupla's. So you still get pretty good performance, but it can be a pretty big sweep, especially if there's pathological cases. If you use very small tiles, then it doesn't do very well. So I'd say in general, it still does pretty good, but there's a lot of performance on the table, especially with respect to the tile sizes that you can recover by doing the tuning. The other kinds of hints, like those optimization hints, those are for like very small last couple % of performance. Those ones don't necessarily affect things much, but the tile sizes really can have a big effect.
Anybody else? All right, I think we have reached the end of our questions and the end of our meeting. Thank you, everybody, for coming. A big thank you to our presenter, Ezra, tonight. I personally was very fascinated by your presentation.
Yeah. Well, turned on. Okay. Yeah, well, thank you. Oops. Thank you, everyone. It was really great to present here. So I really appreciate you inviting me. And maybe I'll also invite for other, MWCPP talks.
Yes, next time I'll try to have my own HDMI cable.
Yeah. Great. And if you have any questions for me, let me know and